Hi everyone, I'm Suprovat Ghoshal. I am a postdoc at University of Michigan. Today I'll be talking about our work, which is titled A Characterization of Approximability for Biased CSPs. This is joint work with Euiwoong Lee, who is my host at University of Michigan. Now, I'll begin by describing the basic objects that we study in this work. So these are Boolean Max-CSPs, which are Boolean maximum constraint satisfaction problems. They are very well known in the literature, but let me just begin with a very elementary definition of it. So Boolean Max-CSPs are combinatorial optimization problems, which are can be thought of as hypergraphs over vertices, which represent variables, and edges, which represent constraints. And in particular, the constraint associated with a fixed edge is actually determined by a predicate associated with that edge. So for any edge E, we will associate a Boolean predicate, psi of E, with that edge. And that would determine what values assigned to the vertices would be considered as accepting assignments for that edge. And with this comes the notion of labeling satisfying a particular edge. So in particular, edge would be satisfied by labeling if the values assigned to the vertices by the labeling make that predicate evaluate to 1. In particular, if we are thinking of Boolean labeling sigma to the vertices, and we are looking at an edge I1 through IR, being the vertices of the edge, we will say that sigma satisfies the edge I1 through IR if psi E evaluates sigma I1 through sigma IR to 1. That is, sigma I1 through sigma IR form a string which is in the pre-image set of this string, of this predicate. Now, overall, the goal of this problem is to find a labeling of all the vertices which simultaneously satisfies the maximum fraction of these edges. Now, this is a very commonly studied problem in theoretical computer science. They're almost everywhere, starting from classical results like the Cook-Levin theorem, all the way up to very sophisticated results such as the probabilistically checkable proofs theorem. They are very versatile and expressive. They can express several problems such as max cut, max sat, label cover, unigames, among many others, which are on their own very well studied problems. And consequently, it's not surprising that some of these are actually very closely connected to some of the major open questions in complexity theory, such as the unigames conjecture or the exponential time hypothesis. Now, this work deals with a slight variant of Boolean Max-CSPs, which we call biased CSPs. So let's see what these are. So biased CSPs are still, the setting is we again have Boolean Max-CSP. So it again comes with a constraint hypergraph. Vertices are variables, edges are constraints. But now there's an added twist. The twist is that we are looking for labelings which satisfy as many constraints as possible, while also respecting the global constraint. That is, the labeling must have at most k ones. In other words, we are restricting the search space of the labeling to be among labelings which have at most k ones, and we want to output the best labeling out of those. Now, throughout, we will think of this relative fraction which upper bounds the number of ones in the labeling as the bias of the instance, and we'll denote it as this parameter mu. And along with that, we'll also notice that now that we have restricted, put a constraint on the instance that the labelings have to have at most mu fraction of ones, that makes the maximum value achievable for that instance a function of the bias parameter. And therefore, we will think of the optimal value achievable as a function of the bias parameter, which will make various other things about the problem also expressible as a function of the bias parameter, as we'll see soon. Now, let me take a moment to convince you that bias CSPs aren't exactly new. And in fact, many well-known problems that are studied on their own fit into the framework of bias CSPs quite naturally. And in fact, we can recover their definitions just by instantiating this definition with the simplest of Boolean formulas. For example, let's take max-k coverage. So max-k coverage, I claim, is just a bias CSP with OR constraints on its edges. Why is that? So recall that the OR formula is satisfied if and only if at least one of the inputs is 1, right? So this tells us that we are essentially trying to find k1s in the graph, which makes sure that as many edges have at least one in their configuration. So this naturally lets us reinterpret the bias CSP objective on OR constraints as the following, where it's just saying that we want to find k vertices in the hypergraph which hits as many edges as possible, which is exactly max-k coverage. On the other hand, change the OR constraints into AND constraints, and we'll get Densest-k-SubHypergraph as another problem that can be expressed as a bias CSP. Again, how is that? So think of a bias CSP which has AND formulas on its edges without negations. And recall that an AND formula can be satisfied if and only if all the inputs are 1. So again, what does this tell us? This tells us that we are in the bias CSP objective trying to find k1s in the graph, in the hypergraph, which makes sure that as the maximum number of hyperedges have all their vertices labeled as 1s, which is again the same as trying to find k vertices in the hypergraph which induce as many edges as possible, which is again exactly the Densest-k-SubHypergraph problem. So now modulo these couple of problems, one may ask that why do we want to study these problems in a more generic framework? And towards that, let me give you a set of compelling reasons, hopefully compelling reasons for why we should study these problems systematically. Firstly, including the two problems that we just saw, max coverage and Densest-k-SubHypergraph, there are several others like max bisection, min bisection, and several other related problems which do not directly fit into the framework of max CSPs, but naturally fall into the framework of bias CSPs because of this global constraint on the number of variables that can be assigned a particular value. And because of that, the well-rounded understanding that we have for max CSPs does not translate to the world of biased CSPs. And consequently, for many of these problems, we actually have a far from complete understanding of their upper and lower bounds in terms of approximation guarantees. Moreover, studying other problems in this framework allows us to kind of do a beyond worst case kind of analysis. For example, let's again take Densest-k-SubGraph. It is under various hypotheses known to be a really hard problem to solve, but then one can ask, is it that Densest-k-SubGraph is hard to solve for all possible k's, or maybe it is easy for some k's and it is harder for some others? And mainly, also we want to understand how does the approximability change as a function of k, right? And studying these questions, studying these problems systematically allows us to actually understand these questions in particular allows us to address the question of how does the approximability of a problem change depending on the relative fraction of ones that we are allowed to select, and so on and so forth. And finally, it turns out that these problems and several min-unsat variants of biased CSPs are very strongly connected to the small set expansion hypothesis, which is again a major open question in complexity theory. And understanding these problems would only allow us to understand the small set expansion hypothesis better, and might give us alternative ways of addressing this question. So now in this broad agenda for biased CSPs, let me now state the main questions that we seek to answer in this work. So the first question is one of coarse characterization. So what does that mean? So let's take our running example of Max-K coverage and Densest-k-SubHypergraph. So it is quite well known that Max-K coverage has a 1 minus 1 over E approximation algorithm that works for every K. So in particular, this tells us that there is a K or mu independent approximation algorithm for Max-K coverage. On the other hand, if you look at Densest-k-SubHypergraph, it's a really hard problem to solve. In fact, it is known under several reasonable complexity theoretic hypotheses, such as the small set expansion hypothesis and the exponential time hypothesis, that there is no constant factor approximation algorithm for Densest-k-SubHypergraph or even Densest-k-SubGraph. So what does this tell us? It tells us that, of course, the approximability of a problem, the approximability of the biased CSP for a choice of a predicate depends on what the predicate structure is. And simply changing making the predicates for biased CSP from or predicates to and predicates, that can make a problem go from constant factor approximable to not admitting any constant factor approximation. So what we hope to do is to understand this behavior a bit more systematically, where we want to maybe establish a dichotomy of sorts, where we want to say that maybe it's the case that either biased CSPs for certain predicates can admit constant factor approximation algorithms, or it's the other way around, where there is no constant factor approximation algorithm for some other predicates. And we want to understand what kind of predicate structure governs this kind of behavior. Now, in fact, we actually don't want to stop there. We want to go a step further. We want to get a finer understanding of how the approximability of a biased CSP for a predicate changes as a function of mu, as an explicit function of mu. Formally, what we want to do is we want to understand the bias approximation curve of a predicate. So in particular, we want to understand this quantity alpha mu of psi, which is basically the best approximation factor that we can hope for using polynomial time algorithms for biased CSP instances with predicate psi and subject to the bias constraint with bias parameter mu. And the hope is that we would be able to give explicit upper and lower bounds for the bias approximation curve as a function of the predicate and the choice of the bias parameter mu. Here, upper bounds would mean approximation guarantees, lower bounds would mean hardness approximation guarantees, and the best case would be that we'd have matching upper and lower bounds. And these are actually the questions that we answer in this work. We make substantial progress towards answering these questions. So before I can state our results, let me set up some notations that will be useful in stating the results. So the setup is, let's say we fix a predicate, an arity Boolean predicate, And with that, we'll associate a bunch of things. So firstly, we have this set psi inverse of 1, which is basically the pre-image set of the of 1 under the inverse mapping. So it's basically the set of strings which make the predicate go to 1, or it is more popularly known as the set of accepting strings of the predicate. Now, given this, we want to define a set of minimal accepting strings in the set of accepting strings. So how does this minimality come about? So let's think of the following partial ordering between Boolean strings. So let's say we take two Boolean string, beta prime and beta, and we will say that beta prime is preceded by beta under this partial ordering if the set indicated by beta prime is contained within the set indicated by beta. So this now, of course, defines a partial ordering among the set of accepting strings for the predicate. And with this partial ordering, we will identify the minimal elements as the minimal accepting strings for this predicate. And finally, we have this notation, script S of I, which is basically denoting the set of R length Boolean strings of Hamming weight exactly I. Now, these are all the notations that we need to state our results. So let's now move on to our first result. Right? So as promised, our first result is the one related to coarse characterization. So here we show the following. We show that assuming the small set expansion hypothesis, biased CSPs on predicate psi are constant factor approximable for every bias less than half. If and only if M of psi is contained within the sets S0 union S1. So in words, this condition is the same as asking for the following, that we want all the minimal accepting strings for the predicate to be having Hamming weight at most 1. So they must be contained within the first two levels with respect to the weights. Now, let's see, how is this useful? Let's maybe use this to recover some previous known results that we already know from previous works. For example, let's again take our running thread of max-k coverage and Densest-k-SubHypergraph. Now, max-k coverage, recall that we argued that this is just biased CSPs on OR constraints, and OR formulas again accept a string if and only if at least one of the inputs is 1. So this can naturally be then used to argue that the set of minimal accepting strings for the OR predicate is exactly the set of one weight strings. So it's basically the set of strings which have exactly one position set to 1. And clearly, this is a set which is contained within the set of all strings which have Hamming weight at most 1. And therefore, our characterization says that max-k coverage does admit a constant factor approximation algorithm, which again supports what we know from previous results. On the other hand, if we take Densest-k-SubHypergraph, recall that Densest-k-SubHypergraph is again a biased CSP with an AND constraint on the edges, and the AND formula has just one accepting string, which is just the all-one string, and the all-one string is clearly not it clearly does not have Hamming weight at most 1, so it fails our characterization. And that means that our characterization implies that Densest-k-SubHypergraph cannot admit a constant factor approximation algorithm, which is again something we know from previous results. Now, the cool thing about this is while these previous results do establish these special cases, we get this characterization for all possible predicates, where we get to say that either a predicate would admit a constant factor approximation algorithm, or it doesn't have any constant factor approximation. And this is based on a very clean combinatorial characterization that is very easy to check. Now, next comes the final characterization result, which is the following. Here, informally, we show the following, that take the bias approximation curve, which is denoted by this quantity alpha mu of psi. This can be related to the bias approximation curve of the Densest-k-SubHypergraph problem. Now, formally, what does this imply? Formally, it actually implies a somewhat complicated looking expression. So let's take a moment and unpack what this expression actually is saying. So the left-hand side is, of course, the best approximation guarantee that we can hope for mu biased instances. And the right side is minimizing over choices of betas, where betas are minimal strings, minimal accepting strings. And it's looking at the Densest-k-SubHypergraph bias approximation curve of the additives given by the weights of these strings. And the asymptotic notation in the middle is just saying that the two things are related up to multiplicative factors of R. And now, overall, in words, what this is roughly saying is that the best possible approximation factor for a biased CSP on predicate side for a fixed choice of mu is somewhat equivalent to the bias approximation, or rather the best approximation guarantee that we can get for Densest-k-SubHypergraph, up to with the same bias constraint, but with an arity which is determined by the weights of the strings in the minimal set. Now, this of course still looks arcane. It is still not really very enlightening because of, it doesn't give us explicit bounds on what the bias approximation curve of a predicate actually looks like, right? And in order to remedy that, we'd have to see if we can give explicit bounds for the bias approximation curve for the Densest-k-SubHypergraph problem itself. And that is our third contribution in this work. So we give explicit upper and lower bounds for the bias approximation curve of the Densest-k-SubHypergraph problem. We show that for Densest-k-SubHypergraph of arity R with k equals mu n, there is an efficient mu to the r-1 log 1 over mu approximation algorithm for it. And we support it with the lower bound, where we show that assuming the small set expansion hypothesis, Densest-k-SubHypergraph is hard to approximate to a factor of r cube mu to the r-1 log 1 over mu for similar instances. So overall, what this does is ignoring constant multiplicative factors, it gives matching bounds up to a factor of r cube, where r is the arity of the hypergraph. And in particular, when r is constant, we actually do get matching bounds up to constant factors, which actually gives like the first matching bounds for the Densest-k-SubGraph problem itself. Now, let's see how these bounds are actually useful in the end, right? So if we combine the upper and lower bounds from the previous slide, so together they kind of imply this, that if you look at the bias approximation curve of the Densest-k-SubHypergraph problem of arity R, that is up to multiplicative factors of R, the same as mu to the r-1 log 1 over mu. And once we plug this into our previous characterization, which related the bias approximation curve of a general predicate with that of a set of Densest-k-SubHypergraph problems, we get this, that the best possible approximation guarantee for a predicate on with bias constraint mu is actually mu to the i-1 log 1 over mu, where this I is basically the worst weight, that is, it is a maximum weight of any string in the set of minimal accepting strings. This explicit expression is the sum total contribution of the various parts that we saw throughout our talk: the coarse characterization, the finer characterization, the explicit bounds for the Densest-k-SubHypergraph problem. So all these things taken together imply this bound for the bias approximation curve for any predicate. And in particular, we get that we have matching upper and lower bounds, matching algorithms and hardness for every biased CSP whenever the IIT is a constant. And this is the final main key result that we have in our paper. Now, before I finish our talk, I'll quickly go over some very elementary ideas that are used, like very basic ideas that form the basis of the various arguments used to prove the various results. In particular, firstly, the connection between bias approximation curve of a predicate and that of Densest-k-SubHypergraph comes through this connection which uses the level weight predicates, or what I call as the symmetric predicates. So in particular, let's think of the ith symmetric predicate, which is the predicate which accepts if and only if the weight of the input is exactly I. Essentially, it is a predicate which whose behavior is just depends on whether the predicate has a fixed weight or not. And morally, what we end up spending most of our time showing is that the bias approximation curve of the ith symmetric predicate is somewhat similar to the bias approximation curve of Densest-k-SubHypergraph problem of arity I. So in other words, the ith symmetric predicate on biased CSPs behaves similar to Densest-k-SubHypergraph problem of arity I. And this is kind of the key idea that goes into connecting the bias approximation curve of a predicate with that of Densest-k-SubHypergraph. And of course, we do this by showing a chain of reductions which go to and fro between the two problems, which allow us to prove a lower and upper bounds of the bias approximation curve of the former with the latter. And algorithmically, for Densest-k, like now that we reduce our problem to understanding Densest-k-SubHypergraph, we use a combination of techniques to derive explicit bounds here. In particular, our approximation algorithm uses ideas for an algorithm for Max-CSPs from the work of Manurangsi, Nakiran, and Trevisan. We use reduction to show the hardness of Densest-k-SubHypergraph, which is a dictatorship test based. So it's basically a noise stability test on the biased hypercube, and its analysis uses several Gaussian noise stability bounds from the work of Kote and Saket. We also use techniques from the work of Raghavendra Stoyer and Tulsiani to compose this dictatorship test with the small set expansion problem as the outer verifier. So these are the broad techniques that we use in our work. So just now to summarize, in this work, what we do is we give a clean understanding of when biased CSP on a predicate is admits approximation algorithms that are independent of the bias parameter. We go a step further. We give explicit bounds for the bias approximation curve of the Densest-k-SubHypergraph problem. And of course, the bounds that we get for the Densest-k-SubHypergraph problems are matching up to multiplicative factors for constant arity. And this consequently also gives us matching bounds for every biased CSP of constant arity. So overall, I'll just quickly end by concluding with a few broad threads that I feel like are fundamental questions that need to be understood in order to understand biased CSPs better in this framework. So the first question is, while our current work gives somewhat matching bounds, which are matching up to multiplicative constants for a fixed arity, we don't exactly have matching bounds once we take the constants and the dependence on arity into account. So of course, the holy grail here would be to understand optimal algorithms and hardness for every biased CSP. Along with that, another interesting question here would be to understand biased approximation resistance in the following sense that when is mu biased guessing an optimal algorithm for a biased CSP? This would be a natural generalization of all the things that we know about the optimality of uniformly random guessing in the world of CSPs. And finally, another important thread here would be to understand whether any of this framework translates nicely to the world of continuous optimization and real valued predicates. So there are various problems in the continuous optimization world, which are also problems which have like local objectives and global objectives. And there's often like a smooth trade-off between the two. And hopefully some of the techniques and the framework introduced here can be used to address some of these questions in the continuous optimization world. So this concludes my talk. For more details, please listen to the live talk of the same, as well as please do come visit us at the poster session. We'll see you at STOC 2022. Bye.